isolate each Korsakoff and see which ones uniformly contract. Or expand it, and we proved that this set is always an open cone, and an element was uniformly partially hyperbolic in the sense of this definition, EC partially hyperbolic, if it either expanded or contracted every Korsakoff foliation. So it's the intersection of these symmetric open cones. Today I want to spend 5 or 10 minutes, hopefully, discussing sort of the measure theoretic side of this to give this a bit more structure. And then I want to go into some rigidity questions related to this. And to do that, we need to talk about what Osciletta's theorem looks like in higher rank. So what is Osciletta's theorem? For abelian actions look like? Well, I now have many different directions, right? I still have a Lyapunov splitting, but the rate of expansion or contraction is going to depend on the element I choose. So I need a way to associate, given an element, what's the Lyapunov exponent of that element? And it turns out this relationship is always linear. And this extends what happens in the real case. So there exists a finite collection, I'm going to call delta, in the dual space of Rk cross ZL. So these are functionals on Rk cross ZL. And the splitting of the tangent bundle. Now I don't even want to isolate the central distribution. I could do that, but I really want to isolate the orbit distribution of Rk, because this one's going to be special. This is truly 0 exponents. There may be other 0 exponents, which I'm going to put over here, plus the sum over all chi and delta. So I'm going to call my Lyapunov exponents chi, E chi mu. And I forgot to say one thing, that I want to assume that alpha preserves a measure mu. Because these functionals, just like the Lyapunov exponents of a diffeomorphism, are going to depend on the measure that you choose. It's not an unreasonable assumption. Yeah, okay. Yes, every abelian action will preserve some measure. So we'll always have these floating around. Later on, I'm going to assume that we're preserving volume. So I'm going to set on that. And we're actually going to see a lot of rigidity, assuming that the set of partially hyperbolic elements are dense. So I have the splitting such that if I take an element of E chi mu, of x, such that, for almost every x. So if I look at a full measure set of points and I take a vector in that distribution above that point, I get the following. Let me write it up here so it's nice and big. So the limit as the norm of A goes to infinity, not just as I iterate a single element, but I can take sort of a winding curve that goes out to infinity uniformly. I want the log of the norm of d alpha A v. So this I want to grow like, alpha of A v. I said it right, but wrote it wrong. All right, so I see how quickly this thing is growing. I want it to be like chi of A. I divide this by the norm of A, and this turns out to be 0. So this is like extending the notion of a derivative in terms of f of x minus f of y divided by y minus x, and taking a limit as x goes to y. and turning it into a linear approximation, right? So this is the same sort of thing. So this implies that the Lyapunov exponents of the diffeomorphism A are given by chi of A, but it's slightly stronger than that because I'm allowed to more than just iterate a single element. I'm allowed to diverge a little bit. In the diffeomorphism case, yes. There are counterexamples if you take a generic cocycle. You can look at the paper Smooth Ergodic Theory of ZK Actions. So a good reference for this is Brown, Rodriguez, Hertz, and Yuan Wang. They have a long tome of a paper called Ergodic Theory of ZK Actions, and this is the first topic they tackle, is a proof of Osseletti's multiplicative ergodic theorem, and they warn that there's some weird examples that happen outside of L1. Normally, you just need L1 for the Z case, but there's something weird that happens. L1 cocycle. So you look at the matrix cocycle, you take the log of the norm of the matrix. I'm talking, for a derivative cocycle.
That's what you meant by diffeomorphism.
Yeah, exactly. So for a derivative cocycle of a diffeomorphism, this is always going to be fine. For a general cocycle over a measure-preserving system, you need to be a little bit careful. But in our context, we're always going to have this.
Ergodic.
Sorry?
The measure is supposed to be ergodic, right?
Yes. Thank you. And ergodic. Thank you. You have the ergodic decomposition theorem for RK cross ZL, so once you have a measure, you have an ergodic measure as well. All right, so what's the key takeaway from this? How does this interact with what we talked about before? So the thing I want to note is that for every coarse-Lyapunov foliation, the tangent bundle to W, and remember, W itself is a common stable manifold, right? So this is WSA1 intersect WSAN. The tangent space to W has to be inside of the stable manifold for the common stable manifold considered as a ergodic thing, right? So this is a subset of the direct sum over all of the AIs, over all of the chi's such that chi of AI is negative of E chi of mu. And this happens for every ergodic mu. No matter what. When the action is a Nosov, I really get equality. Right? Because the central distribution is the tangent distribution, so I can't expand or contract along that by local freeness. So what does this say? This says that each oscillated space, sorry, that's not quite right. So I need one more definition. Given one of these functionals chi and delta, I want to let C minus of chi, be the set of things that measurably contract chi. So the set of A's such that chi of A is negative. And rewriting this is equivalent to saying that C minus W, right, the set of things that uniformly contract W, is really a subset of the intersection over all ergodic measures mu for alpha, the intersection over all E chi's mu's, which are subspaces of TW of C minus chi. No. So I'm looking at all the chi's such that chi mu is a subset of here, right? So I fix a measure, and then I look at that measure and look at all the chi's. So this should probably be the set of chi's such that E chi mu is a subset of TW. So this chi does depend on the measure, yes, in that sense.
Oh, I see.
Right, so these are all half spaces. I have some evidence to suggest that this should be true in this way. I've had some discussions with people here that suggest the simple proof is possible, but I don't want to claim it. I think this should be an equality, which would be really nice, right? It would tell us that this is some infinite intersection of half spaces. It should certainly be true in the Anosov setting. That I'm quite confident in saying. I haven't written down a proof. What do I want to observe? I want to observe one last thing before we move on to rigidity. And this is going to be the sort of key that unlocks everything. That if alpha is totally partially hyperbolic, which means, remember, that the set of partially hyperbolic elements is dense, C minus W has to equal C minus chi whenever chi is a Lyapunov exponent associated to W. Right? Because once I intersect two half spaces that are not the same, then I get sort of a cone, a proper cone. And the set of partially hyperbolic elements is going to be the intersection of some collection of cones, and one of them is proper. And there's no way for this to be dense. The only way for this to be dense is for all of these half spaces to be the same. So, yeah.
Sorry, it's going back to my previous question. I didn't understand. But C, the definition of C minus chi.
Yeah. So here, I'm just considering chi as an element of RK cross ZL star, right? This is just a half space determined by chi. Right, so I look at all the measures, I look at all the Lyapunov functionals I get. Each coarse Lyapunov distribution is invariant, right? So it has to split as a sum of Lyapunov exponents, Lyapunov distributions. So for something to be contracting, it has to be stable for every measure, not just one measure, but I'm assuming uniform contraction, right? I have a uniform partially hyperbolic splitting. So this is certainly true, right? If something is uniformly contracting, it's contracting for every measure. That's all this is saying. Right, so what is this saying? It says that every Lyapunov exponent subordinate to this coarse Lyapunov foliation is proportional to something, and each coarse Lyapunov foliation, in fact, has a unique functional up to scalar multiple, positive scalar multiple, because two functionals share the same negative half space if and only if they're positively proportional. So this is a basic linear algebra fact. If you don't know the proof of this, I encourage you to think about it, but I'm going to leave this as an exercise. So since C minus chi1 equals C minus chi2 if and only if chi1 equals C chi2 for some C bigger than 0. If totally EC partially hyperbolic, for every Course-Lyapunov foliation W, there exists a unique functional chi up to positive scalar multiple. And this, remember, is compatible with the Z and R case. This is sort of a trivial relation. The set of functionals on R are just scalars. It's a scalar multiplication, right? This is sort of an unremarkable fact for Z and R actions, but it's a very strong condition for Z Cray cross RL actions, right? So this is the power of totally partially hyperbolic. It gives us to each Course-Lyapunov foliation a unique functional that all of these, so in particular a unique kernel that we can move along. Any questions about this before I move on? This is what we saw in the two examples we talked about, right? We talked about the product example where the half spaces were sort of, the kernels were the axes, and then the SL3R case where we had three functionals associated to the elementary subgroups of SL3R. So now let me start making some more assumptions about my action, which are going to be more and more unreasonable until the very end when I say that they're implied by something. Rather, also maybe unreasonable in the context of abelian actions, but not unreasonable in the context of another type of group action. So here's rigidity. Rigidity. And this is Damjanovic. Spazier, myself, and Dishing Zhu. So what are my standing assumptions? So first, let me just restrict to RK again. I'm just partial to RK actions. So I want to assume that my RK action on a smooth manifold X is totally EC partially hyperbolic with respect to some distribution, volume preserving, and ergodic. This is maybe the most boilerplate set of assumptions. The next one is more unreasonable. I want to define a new term called super accessible. So what does super accessible mean? It means that if I fix any Course-Lyapunov distribution, which I'm going to now identify based on the corresponding functional. So if you give me any chi, and any pair points, x and y, there exists the following picture. So I start from x, end at y, and I sort of draw the usual accessibility picture of moving along stable and unstable manifolds. But now I have more options than just stables and unstables. I want to move along the Course-Lyapunovs. So here's W chi1, W chi2, W chi3, W chi n. So this path can be as long as I wish. The key feature I want is that chi I is not chi for every I. So I want to be able to connect any 2 points, omitting one of these exponents as needed. This is going to relate to accessibility of the kernel actions. Yeah, thank you. Plus or minus. Yeah. E chi, and for all C in the reals. Yeah, that's true. This implies rigidity, so I technically don't need this, but I add it there for emphasis. Okay, this is a strange assumption, but it turns out to be a really powerful one. It's going to imply a lot of ergodic properties. It turns out that this means that there exists an element A in kernel chi such that A is accessible, where you expand the central distribution to include E chi and E minus chi. So this tells me that, in fact, the kernel actions are ergodic as well, not just the RK action. The last assumption, we're getting more and more unreasonable as we go. So this one's going to seem like the most unreasonable. But I want to be unreasonable for now. So for every Coarse-Lyapunov foliation W chi, if I look at d alpha restricted to the tangent bundle of W chi, I want to assume it is measurably conjugated to something of the following form. So e to the C1 chi of A times a rotation matrix, theta 1, e to the C2 chi of A times a rotation matrix, theta 2. And it's block diagonal, right? So e to the Cn chi of A theta n, rotation matrix theta n. So here each theta I is an orthogonal matrix, say SODI, or each of these blocks is di by di. And each of these CIs is a real number. Yes, I want each Coarse-Lyapunov to have this decomposition for every element of the action, right? So d alpha A restricted to the tangent bundle. I only want this measurably, W chi. Right, this is really strong. Even, it's maybe a little less strong than asking for continuous, even though it will imply it in the end. But this is what I want to assume. Now, I don't want to spend too much time on this, but I want to tell you that secretly, in another setting, this is not an unreasonable assumption. So for those of you who know this, it's probably no surprise what I'm about to say. For those of you who don't, I invite you to talk to me or one of the experts about this afterwards. But so the secret main theorem is that if G is a higher ranked semisimple E group, the third condition is free. which is really surprising. This is called Zimmer's co-cycle superrigidity theorem. And also, accessibility implies superaccessibility.
So you mean if you're revealing beds in higher?
Exactly. As a Cartan subgroup. Yes, exactly. So if I have an action of G such that the restriction to an R-split Cartan satisfies these properties, or even just this property, the first one in accessibility, superaccessibility in this property also follows immediately. So this. I don't want to define a higher rank semisimple E group. Oh, oh, SL3R is the sort of SLNR in general. SL2R has rank 1 because the diagonal subgroup only has one dimensional, but SL3R, which we saw last time, is an example of a higher rank semisimple E group. It's the diagonal subgroup, yeah. It's isomorphic to R2. In SLDR, the R-split Cartan subgroup is RD minus 1. That's sort of implied by this, right? Because if k was equal to 1, there would only be one Korsakoff exponent, right? So there's no way that I could have superaccessibility. So I'm going to prove something about RK action satisfying these properties. I'm saying that if I have a G action, I get these properties for free. Right? I just need the first property, ergodic and volume preserving, and accessibility. So that's why I said this is the secret theorem that we're proving. I want to focus just using these assumptions about abelian actions. Yes. This is the secret setup of the theorem. I guess I should state the theorem. So what's the theorem? Okay, that's the next page. I've spent a lot of time setting it up. So theorem. So alpha is C infinity conjugated to a translation of the form A, so translation action, I guess I should say. So we call it beta, is an action of RK on K mod H mod gamma, where A acts on K capital K little h gamma, right? This is a biquotient space by multiplication on the inside. And RK embeds into the centralizer in H of K. So these actions are called bihomogeneous, right? If I didn't have this funny K over here, and we'll talk about this at some point when we discuss elements of the proof. If I didn't have this K, it would just be a homogeneous action, right? It would be like a translation on SL2R mod gamma, which was like a geodesic flow, or the SL3R mod gamma that we talked about as an example of an R2 action that has no rank 1 factors. This is similar. I'm just now having the quotient on the left by a compact group. So in the secret main theorem, I just replaced this RK by G. So G is also bitranslations in this bihomogeneous structure. And secretly, I'm omitting a few things. I need to pass to a finite cover. But I want to avoid the discussion about passing to finite covers if necessary. Or if possible, rather. Right, so this is a rigidity theorem. It's saying, with these assumptions, I can't really do much. My dynamics have to live in a finite dimensional family. And in fact, it's even more than a finite dimensional family, right? The set of homogeneous spaces like this, when if G is higher rank, that's going to have to embed inside of H, right? Because it's by translations. So the set of higher rank Lie groups are somehow countable. They're discrete, right? They don't have a moduli space. And the set of lattices in higher rank Lie groups is also countable, right? There's not much you can do. So this is really not even in a finite dimensional space. There's only really some discrete set of actions you can take. There's not very many actions. It's highly restricted, the type of actions that you can have. Yeah? No, you can. You can have huge dimensional EC. So included in this example is something like, well, I could take, say, SL3R acting on SL 10 to the 100 R mod gamma, right? This is going to be accessible. It's going to be even super accessible if it's just acting in the top right corner. In fact, any embedding of SL3R into SL 10 to the 100R is going to be one of these examples, a prototype of this theorem. Yeah. So the central distribution can be quite huge. This is one of the upgrades we had to our original theorem, where we had to assume an Nossoff. But we realized at some point that we could do it for accessible partially hyperbolic. Any other questions before I start going into elements of the proof? H is something we have to build. We don't know what it is. It's a Lie group. It's a Lie group, connected Lie group. I'm assuming my manifold X is connected. Because I'm an RK action, I think that follows from ergodicity. All right, so there are 4 steps of the proof that I want to talk about. Hopefully I have time to comment on all of them. I may spend more time on some parts than others. So step 1 is an application of the invariance principle. There's many names I can put here. I'm just going to put the first and last that I know of. So this was first used by Ladrapier. And then the version we use is by Avila, Santa Maria, and Viana. And I'm not going to give a precise statement because I don't think there's an overarching statement, and you need to check details whenever you want to apply this. But the moral is that over an accessible partially hyperbolic system, invariant measurable objects are actually Holder. The Avila Santa Maria Viana paper shows that this is true for matrix cocycles with one exponent. And you may be looking at this funny matrix I have over here and saying, of course, this doesn't have just one exponent. This has n different exponents, right? Because I have coefficient ci in front of all the chi's. But this is where the superaccessibility assumption comes in. If I choose some a in the kernel of chi, all of these exponents become 0. So I'm measurably conjugated to a rotation, and I'm still accessible by superaccessibility. So I can use an element of the kernel that's going to be accessible partially hyperbolic, and now includes this funny measurable rotation in the center. And it turns out that all of these distributions, which are only guaranteed to be measurable, are going to be upgraded to Holder. And I can choose a metric so that this is actually Holder continuously conjugate and not just measurably conjugate to this type of rotation. Yeah? Okay, if we're in Ossoff, then you get Holder. If you're partially hyperbolic, you only get continuous. You're right, you caught me. Thank you. We only need continuity, so thank you. I keep thinking in Ossoff in my brain because it's easier. Okay, so this implies that the derivative is C0 trivializable. All right, what's step 2? For step 2, I just want to write down one sentence and draw a picture and move on. So step 2 is homogeneous structures on each W chi leaf. And this is what Ralph calls the higher rank trick. It's used in almost all higher rank rigidity theorems. What's the trick? I look at a Korsakoff leaf, W chi of x. I take another point in that leaf. And now, from step 1, I know that everything is continuous, right? All these objects are going to vary continuously. So when I apply an element A, because of accessibility, I know that the kernel action is ergodic. And because I'm in the kernel and this is continuous, I'm basically preserving a continuous metric. So I want to assume that I choose AN in the kernel of chi such that AN acting on X, alpha of AN acting on X, converges to Y. Now this intertwines the structure of the leaves. And it's actually going to converge to an isometry using a technique called normal forms. So the main idea is that I get a transitive isometry group action if I start from a point with a dense kernel chi leaf, because I can get back to any point on the leaf, and it's going to come back, it's going to drag the leaf along with it by an isometry. So this picture is going to imply that the isometries of the W chi leaf act transitively on W chi of X. So this is nice. It tells us that my W chi of x is the quotient of an isometry group by a stabilizer using some facts that the dynamics of RK sort of is going to interact with the isometry group in a nice way, basically by contracting automorphism of the isometry group. We were able to conclude that this isometry group is actually nilpotent, or at least contains a simply transitive nilpotent subgroup. So inside of this is some n chi x, simply transitive nilpotent. It acts simply transitively on the leaf. It means that the stabilizer is trivial for every point. So it's a transitive action still. It still parameterizes the leaf. But right, if say this leaf was isometric to Rn, right, then the isometries of Rn are the semi-direct product of SON and Rn. So we have the same sort of semi-direct product structure. That's what we deduce. And we just want to pull out the nilpotent part. We want to omit the stabilizer. Unfortunately, this compact group isn't normal, so we can't disquotient by it. It's kind of a pain to actually get the simply transitive nilpotent group. I want to brush over this and assume that let's live in a fantasy world and assume it's very easy, that stabilizers don't exist. It's a technical and rather boring part of the paper. Maybe Desheng and Daniela can yell at me for omitting a rather technical and difficult part that we had to work on, but I think it's one of the less interesting parts. This is all I want to say about this. Now I want to go to step 3, which is sort of one of the more difficult steps, and one of the ones, it's the step where this mysterious group K appears. So this is constructing an extension. So we have these funny, simply transitive nilpotent groups parameterizing the leaf, but notice that I index the nilpotent group depending on x, right? For each x, I have a simply transitive nilpotent group acting on the leaf. I want to somehow glue these together into a big action on the whole space. And there's a problem with this, even in some nice examples. So our goal is to glue the n chi x actions into a single action. And there's a big problem in that this isn't even possible in some models. And I want to go through a baby case of the model to show you what's happening. So what's the baby case? Let's look at geodesic flow on a hyperbolic 3-manifold. Well, a hyperbolic 3-manifold hyperbolic space is itself a quotient, right? Has this group of isometries. And you might expect that you would just take the diagonal action on this, and you would get the geodesic flow. The issue is that this is not the unit tangent bundle to hyperbolic 3 space. This is the unit frame bundle, right? The orthonormal frame bundle. So you have to do something here, which is quotient by the unitary diagonal subgroup, either the I theta, either the minus I theta. You have to quotient by the circle, right? You can imagine I have my hyperbolic 3 space, I have a frame. I just want to identify all the frames that I get by rotating transversally to the direction that my distinguished vector is pointing in, and the other two I can rotate in. So this is really an S1 bundle. The frame bundle is an S1 bundle over the unit tangent bundle. Now, what happens if I try to define an action parameterizing the horospheres, right? The horospheres here are R2, right? They're stable and unstable spaces. So when we try to parameterize horospheres, parameterize horospheres, we want to use the action of the upper and lower triangular subgroups, right? So 1z, 1, 0, acting on this. But this action doesn't exist, right? So this action is bad. So why does this action exist, the diagonal subgroup action here, but the other one doesn't? Well, if I look at this action, this group, e to the t, e to the minus t, commutes with the unitary diagonal, right? But this group, the unipotent subgroup, is normalized by this, but it doesn't commute with it. And this is going to be the common feature of all the Korsly-Lyapunov foliations as well. They're going to be normalized by some compact group in a fiber bundle we build, but they won't commute with it. Right, so we have to deal with this annoyance. Notice that if all the foliations are one-dimensional, there's no way to rotate within them. And this doesn't appear when you have one-dimensional foliations. It only appears with this higher dimensional setup. So let me just write something down. So this persists. Persists in other translation models. On K mod G mod gamma. Right, so another way to say this is there's no horospherical action for geodesic flow on hyperbolic space, but there is a horospherical action for frame flow on hyperbolic space. So how do we resolve this? Well, this is the start of a complicated construction. I'm not going to give details. But I will give a rough sketch of how to resolve this. And basically, you need to build a fiber bundle over your space. So we need a fiber bundle. And we need to lift our action to this fiber bundle. Let's, for simplicity, so simplifying assumptions, these are, of course, very rarely, and one of them is never going to be true. I want to assume that we only have one exponent. Otherwise, I need to do this procedure simultaneously for all exponents. And I want to assume that there's only one Lyapunov exponent. So write conformal on E chi. This is going to make some of the setups and things I described much easier and manageable, but we have arguments to extend this beyond this assumption. So with these assumptions, what do I want to do? I want to say to each point in X, I want to build the compact group fiber. So K sub X tilde is going to be the set of all framings phi, which go from RD to the tangent bundle at X to W chi, such that if I look at the image of the standard basis, this is an orthonormal frame of Tx W chi. Right, so it's basically, I want to dualize it for reasons of defining the action later. It will become a bit easier. But you can think of it as a set of orthonormal framings, not of the whole space, but just of this coarse Lyapunov foliation at the point X. Right? To each such function, I can associate an orthonormal frame. To each such orthonormal frame, it induces a linear map from RD. Now notice that SOD, and let me add the word oriented. I want to assume that everything has an orientation. This is where that finite cover business needs to be resolved earlier. I want to assume that all these foliations are oriented so that I really have an SOD and not just an OD group. So this acts transitively. On each K tilde X by well, what can I do? If you give me an element of SOD, I can precompose this function phi by my matrix K. And because I want it to be an action on the left, it's really a K inverse. So it turns out because all of these groups or these metrics are continuous, and in fact the metrics are Holder along leaves. We need this a bit later. But this X tilde, we can build a fiber bundle from this. Where I just glue all of these fibers together above a point. And in fact, it's a principal bundle. So this is a principal SOD bundle. And it has some strong regularity along coarse Lyapunov leaves. But is generally only continuous in the central direction. Now I need to define how to lift the action. And this is where the conformality assumption is going to make my life easy. So I want to define an action Rk acting on x tilde by A acting on phi. Remember, this is a framing, so it's gonna, I need to input a vector. Phi of v is a vector based at x. I can push it forward using alpha. Now this is a vector based at ax, but it's not unit length, right? But I know how lengths expand and contract exactly, right? So I can make it unit length just by canceling out the growth. So this lifts the action on the base to the cover, right? If this phi covers x, then this image, right? This is a function a dot phi covers ax. So I push a framing based at x forward to a framing based at ax. And notice that we have the key property that we want in the end. So notice, so A commutes with SOD. I just realized I have only 1 minute left, so there's some procedure you need to do to pass to a proper subbundle. And in fact, I think I'm going to save step 4 to start off the last lecture and maybe use the first 20 minutes of that lecture to wrap up the rigidity theorem and talk about the non-rigidity stuff after that, rather than try to cram it into 30 seconds. So I will thank you for your attention. Yeah.
You, question? Question?
So this is, yeah, so we asked, the distributions in leaves are only Holder continuous, so how do you get a smooth nilpotent group action? So it's true that the foliation, the Course-Lyapunov foliations are only Holder, but the leaves of the Course-Lyapunov foliations are smooth. And I sort of brushed over this, but there's a tool called normal forms that's sort of purring under the machine that's upgrading this regularity. The transverse regularity doesn't affect anything, right? Because if I have, the key fact is that I have a sequence of smooth manifolds that are converging to one another continuously. And the normal forms turns everything into a polynomial. So I have a sequence of polynomials that are continuously varying but converging. So in the limit, I have a limit of continuously varying polynomials, but I don't care about sort of the transverse regularity. I only care about what the map is when I come back to the leaf. So the transverse regularity doesn't matter here. It's really just when I return to the leaf.
More question?
Yeah, let me even make it simpler. G is simple in higher rank. I don't want SL2R cross SL2R. Yeah, you're right. I was a bit careless here. So genuinely higher rank is the better term here.
More question? Now. No, thank you again.